In a previous lesson on functions, a function was defined as a way to analyze two unrelated sets of numbers. By now you should also know that a function could be linear or nonlinear. However, because by definition a single linear function runs in one direction only, towards positive and negative infinity, you don't have to find the limits of linear functions. Therefore, we'll concentrate our analysis on nonlinear or curved limits of functions. Limits are found all around us in both the physical and abstract. For example, highway lanes are all of the same width. This of course puts limits on how vehicles are designed. But the limits of functions are of the abstract type. The limits of functions are defined according to how the curve of an equation changes direction. For example, this equation, when plotted, gives us a curve that moves down from left to right. It hits a low point and then keeps moving from left to right, but this time going up. As the curve moves, and because it is a curve, the slope of the curve changes from point to point. As it moves, if the points are close together, the change in the slope is small. But if the points are wider apart, then the change in the slope is large. So just as the coordinates of each point define the curve, the slope at any point of the curve defines the limit of the curve. Now, because tangents are perpendicular at the point of contact of a circle, and it follows that any curve could be made part of a circle, then a tangent at any point of the curve is really the slope of the curve at that point. And the peculiar thing is that the tangent and slope changes at every point. And you ask, who cares? Well, there is great interest by a lot of people in knowing or predicting when things are about to change. Predicting change is the most important part of making decisions. So limits are important because limits in a dynamic, changing environment tell us that things are about to change. You see, we change because we reach a limit. We have to go in another direction because we can't go any further. So limits and change go hand in hand. As we study nonlinear functions, we must understand limits. The first person to understand limits and directional change was Isaac Newton. As he studied the gravitational pull of the Earth and other physical curiosities, remember, gravity is a non-linear phenomenon, he generated, at the same time, the mathematics needed to explain it. This is how he got around to discover differential calculus, which some academics claimed it was improperly named. Some call it the math of change, and still others call it slope finding. In any case, the study of calculus begins with the limits of non-linear functions. The most popular example used to show abstract limits is the tangent. But before we get to the tangent, there is of course the secant. This explanation of limits uses a moving secant that turns into a tangent. The idea is to find the linear equation of the tangent at a particular point of a parabola. The parabola we will use is y equals x squared. The function of this parabola has the vertex at the origin and is bisected by the y-axis. So it is the simplest parabola you could use. The slope of the tangent we will find is the one at point 1, 1. As you can see, in the parabola y equals x squared, when x equals 1, y equals 1. So it fits. The parabola crosses point 1, 1. Anyway, if we pick 2 points on the parabola and draw a secant, the slope is found using the traditional slope equation where the difference of y over the difference of x yields the slope. As we make the slope smaller by getting closer to point 1, 1, the slope gets smaller. Let's look at the diminishing values of the slope. First, we use the table to keep track of the x and y values. We already said that when x is 1, y is 1. And if we use 2 when x is 2, y is x squared or 4. Now for the smaller values. When x is 1.5, y is 2.25. And when x is 1.1, y is 1.21. And when x is 1.01, y is 1.0201. And when x is 1.001, y is 1.002001, and so on. Let's now find the slope of the first secant made by points 1, 1 and 2, 4. Substitute the values in the equation, and 4 minus 1 is 3, and 2 minus 1 is 1. The slope of the first secant is 3. This table shows the values of the diminishing slope for the other secants. Notice that the slope gets smaller and smaller, but will never reach the value of 2. We can also do the operation by using points coming from the underside. Coming from the bottom, the slope gets larger. This table shows how the slope coming from below gets close to 2, but never reaches 2. This begs the question, why don't you use the obvious point 1, 1 to find the slope? Well, if we use 1, 1, the equation turns into 0. We don't want that, and this is where limits become important. We can get as close as we want with the slope from the top and bottom, but not to the point itself. That's the limit of the function. Well, anyway, but by now you must have realized that the slope of the tangent at 1, 1 has to be 2, because that is where the limit is heading. Therefore, we can now write the limit equation, limit of the function x squared as x approaches 1 equals 2. Now, by using the y-intercept equation, y equals mx plus b, and because the slope is 2 and the y-intercept is -1, the equation of the tangent is y equals 2x minus 1, where 2 is the slope and -1 is the y-intercept.